Good afternoon. Today I'm going to talk about a project that we have started some time back, about a year and a half ago, maybe 2 years ago, that we call Project Muse-Net, which is related to multimedia communication and processing in wireless sensor networks. In fact, this will be a sampling of several lines of research that were started some time back again, and they happen to have this common platform where there is an applicability for each of these lines of work that we have worked on with regard to the multimedia processing and multimedia communication in wireless sensor networks. So. Just an admission just before we begin. Initially, these works have not been started with the intention of creating actually solutions for a multimedia sensor network, but all these solutions happen to support processing and communication requirements for multimedia sensor networks. So let me just give you our vision and how we came up with the multimedia sensor network idea, which is basically not something specific to our group, but there is quite a number of groups that work on multimedia sensor networks. And as you know, the early wireless sensor networks and the research associated with that targets enabling technologies such as sense and send up type of operations, just gather information and deliver it somewhere, and then put some constraint on that, such as maximize the lifetime of the network, and which has been obviously a very important target. However, the wireless sensor networks have been improved significantly over the last maybe 4 or 5 years as well. So first of all, people started adding multimedia sensors. There are several testbeds and prototypes which include multimedia interfaces or sensors on the sensor nodes, including, let's say, the low-resolution cameras or microphones, and still image cameras, infrared cameras, etc. And their use for mission-critical applications has also attracted quite a number of researchers to start working on it. So, while this is a very important leap forward in terms of the envisioning what a sensor network should look like, the constraints have pretty much remained the same. That is, you still have a limited amount of energy resource, and you have limited bandwidth, and really not all that sophisticated hardware. So with this additional this additional functionality that is required of the network, combined with not so different physical resources that you have, actually creates what is really so challenging about the wireless multimedia sensor networks. So here's an idea about what a wireless multimedia sensor network might look like. Let's say you deploy your sensors in an open field, and here I have a military application example. Something is going on here in the network, let's say, in this area. So what you need to do is, first of all, let's say you need to deliver the observation to a base station. Again, the artwork may be a little bit misleading in terms of the scale and everything else, but the idea is something's going on here, I want to report it back to a base station. So how can I do that? So the main issue is, if you have a system set up as such and you are using multimedia sensors, there are several problems you have to overcome. For example, the volume of data that you are generating is much higher than simply presence or absence of a certain signal. So you have to really deliver sometimes kilobytes of data rather than simple couple bytes of data. I mean, if you were to follow the original idea of delivering information over a sensor network. In addition to that, there are obviously certain shortcuts or improvements you can make upon that, but those usually involve quite a bit of processing too. So processing a multimedia raw data is not as simple as just adding 2 numbers and sending the results, or taking the average of a series of numbers. So there's quite a bit of processing involved here too. So here's an observation that we have delivered. The potential of processing the information in a network can be seen as follows. Let's say you have 4 cameras in a given area that have wireless interfaces attached to them, or you can also imagine these to be wireless multimedia interfaces put on a sensor node, and they are basically taking the image of an object in their view field. And eventually what you would like to have at the base station is the type of the vehicle, the location of it, and its speed. Let's say those are the 3 parameters or 3 pieces of information you're interested in. One way of dealing with this problem is really you can take the raw data and transfer it to the base station in its raw form, but as you go along over the multiple wireless interfaces, what happens is the volume of data is accumulated, and you face now 2 problems. First of all, the amount of energy you use to transfer the data is very high. Second, the information delivery takes a long time. So another idea might be, and this is what we advocate to do as an initial step, you can take the data, somehow process it, and decide on this vehicle type, location, and speed here somewhere close to the source of the data, and send the information back to the base station. So the idea is not all that novel in terms of processing the data in the network. This has been proposed for many different systems. What is interesting here is really the fact that the processing that is needed to extract that information is non-trivial. So you have limited resources. How can you use them in the most efficient way to extract that information to reduce the data volume? So this is one of the problems that we want to answer. Well, the properties of the wireless multimedia sensor networks include, for example, the highly variable raw data volume. So you can, if you compare images and audio, you can easily see the difference in the amount of data that is generated by those 2 sources. But in general, you can say that there is an overall high data generation rate. Multimedia data processing is generally considered to be computationally expensive, so we want to do something about that. And resources are not very much different than the regular ones, wireless sensor networks. So here is yet an additional set of requirements. For example, multimedia applications and mission-critical applications require QoS guarantees. Again, although QoS is a very misused term, here I will stick with the term QoS as much as possible, because we really want to limit, for example, the amount of time you spend to deliver the results to the destination, or the maximum amount of energy you are willing to spend to process the data in the network. So those are the constraints you cannot really live without. So, and we see that there are multiple layers involved in QoS provisioning. An example application may state the following task. Let's say you need to report an intruder in at most 5 seconds with 95% reliability, and repeat the procedure every 2 seconds. That is, you're just taking snapshots every 2 seconds, process the information or deliver the information as a whole, and that every report has to reach the destination in 5 seconds or less. And you want to deliver that piece of information with 95% probability, or 0.95 probability. So the translation will be, well, you have, let's say, multimedia data that is generated in X seconds, and then you want to reduce it to a volume A in an additional Y seconds, that is doing some processing internally, then you deliver that volume in Z seconds with 95% reliability to the destination, wherever that your destination is. And by the way, you have the constraints such as X, Y, and Z must be smaller than 5, and X plus Y must be smaller than 2, because you need to repeat it every 2 seconds. So these are your constraints, for example. So what we do here is we introduce 3 lines of functionalities that is necessary, or that we feel is necessary to support a nice multimedia wireless sensor network. First one of them is the in-network multimedia data processing. You get the data from a locality. What you do is you need to reduce the volume of that for communications purposes. Second, once you have the data, either in raw form in one extreme, or completely processed into the result form in another one, in another extreme, you need to communicate data in real time to the destination, and you need to manage your resources in a distributed way with some feedback from a centralized controller. So for this one, I'm going to talk about a solution that we have developed about a year ago, which is called RT Maps. For the second part, I'm going to talk about a protocol, a real-time communication, cross-layer communication protocol we call MMSpeed. And for the last one, well, I'm going to just introduce an introductory work that leads to possibly resource management in such a system. So for the RT maps, the idea is to borrow some of the ideas that have been developed and worked on in parallel processing community for a very long time, and map that in the most efficient manner to wireless multimedia sensor networks, that is, in general, to sensor networks. Here, we would like to work on two different things. First of all, we need to answer the question, why do we need to develop something new rather than just take something that has been out there for a while and directly apply it to here? First of all, the existing solutions do not consider energy consumption. So if you ask, or if you take one of the existing solutions for parallel processing, you will see that there is no consideration for energy whatsoever. Second one, most of the work that is out there is for point-to-point communication links. That is, all processors are directly linked to each other. There is some work on broadcast communication, but they are quite shaky, if you ask me. So, and then we also would like to do scheduling of communication and processing events at the same time. So, do it in a cross-layer manner. So, the RT maps outline includes the minimization of energy consumption of an application subject to execution time constraints. So we would like to finish the execution of a particular algorithm in, let's say, given amount of time, and in the meantime, we would like to minimize the energy consumption of that execution. And this energy consumption includes both energies consumed through while processing the information, as well as when exchanging information among the processing nodes that are the sensors. Here I have to emphasize that the solution that I'm going to present is not specific to multimedia processing applications necessarily, but it is applicable to them. So this is a very flexible solution. If you have any other type of process or procedure that needs to be executed in the network, and if it is parallelizable, then you can use this solution to come up with your own schedules. And we would like to do both task mapping and scheduling at the same time. That is, we would like to find the locations where the information is going to be processed and find the execution sequence.
So are the nodes homogeneous, or do they each have different sort of abilities with respect to processing?
Okay, so for this particular work, we have assumed that they are homogeneous. But this is not an exclusive assumption. That is, we can actually improve the work that I'm going to present here and include other constraints. For example, higher processing power in one node than the others, or different types of communication interfaces if need be. So those can be included as additional constraints to the problem as well. So, but what I'm going to present here is actually a very, very stripped down and a simple version, just for the sake of clarity. And if you go back several slides, you will see also that there are, we also have, for example, a multi-hop cluster solution. And what I'm going to talk about here is a single-hop cluster solution. So this is just for the sake of clarity, that a very simple problem that I'm going to present here. Okay. So we assume that there is an execution scenario that says, well, there's a centralized controller, let's say the sink, that assigns a task to a cluster, saying that, well, align a set of images before sending. If you are familiar with that type of work, you should also be familiar with the image alignment problem. But it's more or less, if you have different sets of data, you would like to see how they overlap in space, let's say, or in time, so that you can actually reduce the amount of data that needs to be transferred. As an example, if you have two cameras looking at an overlapping view field, then you would like to see where they overlap and how a combined image can be formed using that data. So this is a very simple description of that. Then, once this task is assigned to a cluster, the cluster head computes the schedule for execution of that particular algorithm, which happens to be, in this case, image alignment. The schedule is then distributed to all nodes, and application is executed in the network, and obtained information is later on sent to the sink by other protocols. Okay? So the assumptions are quite constraining in this point. First of all, we assume the homogeneity among the sensors. Second one is the single hop clusters. So we have relaxed this condition in our later work, which has appeared a couple months back in transactions on mobile computing. And cluster has schedule and coordinate computation and communication events. We assume that the sensors can compute and communicate at the same time without really inhibiting each other. And we assume also the time synchronization within a cluster to be present, so we are not proposing any solution for that, but we are just assuming it. Whether or not it's a valid assumption can be debated, obviously. And communication is isolated from neighboring clusters. Now, this is something, if you ask me, this is the most constraining assumption that we have imposed on this problem. And we are currently working to relax that and to adopt a more general cluster formation. So the idea is, if you have an application, then you represent it as a directed acyclic graph, and each of these circles over here, nodes correspond to tasks to be executed, and they have a weight in terms of the number of clock cycles they require. They have dependency and communication between these tasks, and the weight of these are represented as number of data bits to be communicated across. So task mapping refers to the assignment of processors, which is, if you have this particular application represented as a DAG, you can either partition it, let's say, into 4 parts and assign these to different processors or different sensors, or if you have another assignment, then you could just split them into 2 and process them on 2 sensors, or alternatively, you could just take everything. So there are different constraints and actually different solutions to the same problem. For the channel model, since we are in a single hop network or single hop cluster, we assume that there's a penalty function that penalizes you if you attempt to communicate 2 pieces of information from different sources at the same time. So if 2 communication events happen to overlap in time and in space, so that there is some interference between them, you have a non-zero penalty, otherwise you have a 0 penalty. Now, in this extreme case, we go for a binary penalty system where we have an infinite penalty if they overlap within the same cluster, or 0 penalty if they don't overlap in time, because everybody is apparently within each other's interference range. However, we can easily extend it to other models where you would be able to account for noise in this in the network if you can predict that too. And this penalty is associated with the effect of, let's say, interference on the final result. That is, if you are working with multimedia data and you have, let's say, certain bits flipped in your original data, and you process it, and this leads to some deviation in your result. If you can predict that, then you can have a non-infinite or a finite amount of penalty associated with that interference.
So this central controller knows the whole structure of the problem. It knows that graph and what the tasks are.
Yeah, the central controller is supposed to know the application. That is the directed acyclic graph that represents it.
But the data associated with the task is in some way spread around the network, right?
Yes, exactly. We assume that the data sources are located within the cluster that executes the information. So let's say there are several cameras within the cluster, let's say in this room. They take a snapshot of the room, and then they start processing that. So the data is not known in advance, and there are some algorithms that have execution lengths that are dependent on the type of the data or the content of the data, but we assume that we can actually come up with either a maximum or worst case scenario and go by that, or in terms of number of clock cycles needed to process that data, or alternatively we can go back and try to find constant time algorithms. So that is, again, a rigidity to the solution that I'm talking about. So in case of a single hop cluster, this penalty function reduces to exclusive channel access, which is a nice thing because now I can actually represent this graph and these dependencies in a very, very compact manner. Let's say you have this particular task graph on the left-hand side, and here, let me just pull it a little bit forward. So these edges correspond to the communication of the result of this particular task to different tasks, so if they happen to be in different nodes. Okay? So these edges are converted to other vertices called nets, and now the weight of communicating that is mapped to this R1 node over here, and the computation tasks are just sitting there as before. Now, these computation tasks are now compounded with the communication tasks. Now we have an additional constraint that the communication tasks cannot be executed on nodes, but they have to be executed on a special processor that is called the channel processor. And the channel processor obviously cannot execute anything but communication. Now all of a sudden the problem is reduced to a very simple original task mapping and scheduling problem well known to the parallel processing community. So the idea is you get the DAG, you convert hyper. If you go back one slide here on this slide, the graph that is called on the right hand side is called a hypergraph, and since it's a directed acyclic graph, we call it a hyperdag. And here we first convert it, then we use variations of known algorithms for task mapping and scheduling to execute and to schedule the communication and computation tasks. Then if there is a DVS capability in the nodes, then we use that to reduce the energy consumption even further. So I'm just going to skip the algorithm part, but let me just give you, tell you very briefly that CMPT, for example, is one of the algorithms that we have used, and it is a very well-known, low complexity, good performance algorithm, and it actually searches for the optimum number of sensors that needs to be involved in computation that gives the best energy consumption within execution time limits. So let me spare you the details here. And we have also an additional algorithm that we have considered, which is called MinMin, which is similar to HCMPT, but which uses a fitness function that trades off delay and energy weights. And the value, the weight value alpha is not known, so we search over the optimal value of alpha, which is actually, our experiments have shown that if you try 10 or 11 samples out between 0 and 1, you find close to optimal solutions that you would achieve for arbitrarily small alpha. So it is basically a parameter-based optimization. So the dynamic voltage scaling is, again, if the processors support that, what you do is you reduce the supplied voltage to the processor, which slows down the processor linearly, but the energy savings goes with the square of the supplied voltage. So, which actually helps you to reduce the energy consumption further in a nonlinear way, which is really good for us, because now if you have, let's say, 2 seconds left in the schedule, so that is your schedule has a 2 seconds of empty time, you can actually stretch your processing through that time and reduce the energy consumption in the during the processing. Now, let me just give you a very simple idea, very brief idea about how what effect this has. here on these plots, on the x-axis we have the deadline, and here in the first plot on the y-axis we have the schedule length, and this over here is what you would get if you were to send all the raw data to a cluster head and let the cluster head execute everything. So as long as you are above this dotted line, this red dotted line, you miss your deadline. Everything else to the lower right-hand corner of this graph is feasible solution. Okay, and you see that these solid blue and red ones are the solutions that we have developed using CMPT and MinMin algorithms, and they actually catch much tighter deadlines than when you would have, let's say, a single sensor dedicated to processing the information. And here on the lower graph, here you have the deadline missing ratio on executed on different random directed acyclic graphs. You see that again for the red one you have almost zero deadline missing ratio for as tight as 22 milliseconds of delay, and for the other one, competitor, where you send everything to a centralized one within the cluster, you have to go up to 36, 37 milliseconds before you can 38 milliseconds before you can actually get results without missing the deadline. Now, on the other hand, we see that the price that we pay for not missing the deadline is higher in consumption. But you can reduce that quite a bit by applying DVS capability, if you have that capability, of course, that you can leverage. Okay. So this is some more information about the energy consumption. So this just tells you how certain things can be done in the network, how certain complex algorithms can be run in the network without actually straining the resources too much. So basically you have both the benefits from processing that in real time, the information, as well as reducing the amount of energy that you need. By the way, so why would we want to spend energy on communication? One of our numerical examples has shown, if you want to communicate, let's say 200 kilobytes of data over 2 wireless hops, this has the equivalent of energy consumption as taking that 200 kilobytes data, basically 4 images, and extracting the location information of an object out of that and executing that in the cluster. So if your source is more than 2 hops away for that particular example, you are better off executing that in the network before sending the result than sending the raw data. And of course, there's a gray area in between, and you can actually go between that. For the second part, I'm going to just briefly talk about MMSpeed, but I'm going to actually go over the basic ideas rather than going through the details. So MMSpeed is something that we have developed based on a protocol called Speed. You may be aware of that, by Tarek Abdelzahir. And this protocol was aiming to deliver information in a sensor network by guaranteeing a given progress speed of information across the network, a physical progress speed. That is, every single time you hop in the network, you actually cover, let's say, 10 meters every second. So there is a 10-meter progress towards the destination every second. So that was fixed. But the way it worked was by dropping packets to regulate the load in the network. So this definitely creates a problem in terms of the reachability probability, right? So you do not know how many of your packets reach the destination. So what we have done is, we have first of all taken the basic idea of MMSpeed, and we created several virtual layers. That is, we started supporting multiple speeds rather than a single speed. Second, in order to give some sort of a guarantee in terms of the reachability probability, we also looked at the probability of, or estimating the probability of reaching the destination by observing the current events of communication and packet dropping in a neighborhood. And with that, we try to give both timeliness as well as reliability guarantees in communication in the sensor network. So here's a depiction of the logical layers that will support the different speeds. For example, you would take a much more lightly loaded path that is shorter, on which you can, let's say, deliver your information at 100 meters per second progress speed. And in a lower set speed layer, you would take a much more congested, maybe longer path to reach the destination. And you do that by looking at the priorities of the packets and setting these necessary priority levels in nodes locally. And these two layers are implemented on the physical network, so on the same physical network. So they both look at the same network. We don't have different nodes. So here is the speed protocol's operation. Here you have, for example, the packet going from I to J, and when it does, it actually covers a certain distance, let's say this much, on the projection of the path from I to K. And if this, let's say, makes 20 meters of progress in 0.1 second, then you have 200 meters per second progress speed. And what we do here is we create different speed layers by using different priorities in the node and create virtual isolation of packets within a single node. And across the node, we adopt a similar strategy in medium access control as in 802.11 by using different backoff intervals for different priorities. For the reliability domain, we use multipath routing in order to provide several different levels of reliability. For example, if you are in a low reliability domain, then your packets would be routed over a single path, whereas where any packet drop would lead to loss of the information. And in a high reliability domain, you would have multiple paths that goes to the destination, and if a packet is dropped, then one of the copies would be delivered to the destination with a higher probability.
Are you creating multiple copy transmissions, or are you just relying on wireless broadcast?
So what we do here is, if we feel like at a local node that we need to, if we compute that we need to deliver multiple copies of the packet, then we are using a multicast session. And this multicast session actually indicates who should forward the packet. And we do not send individual copies. We are trying to reduce the number of transmissions while doing so. So what we do is we send the information, and we only exchange handshake information with only one of the designated recipients, so and the other ones overhear that. I'm sorry?
Only one person.
Exactly, exactly. The other ones simply keep track of whether or not they can receive the information, so that they can say, well, if I am a secondary receiver, I'm not the primary correspondent, then the probability of me forwarding the data is that much, which is accounted for, which is included in the reports that are exchanged between the nodes from time to time. So we look at the local packet dropping or local packet dropping rates, and accordingly we are trying to project how much, what the probability is to for that packet to be delivered to the destination based on the distance to the destination and the local packet drop rate. So, which is obviously a bad prediction to begin with, because now you say, well, my local behavior is going to be repeated every single time I hop across the network. But it is still better than having no prediction whatsoever. So we are actually going a little bit ad hoc in this manner. So there is, these don't necessarily have a direct provable guarantee. So again, in this graph here, for example, I show that if you have a packet with reachability probability requirement of 0.2, you can choose any of these links to forward your data. But if you have a little bit of a higher packet reaching probability, let's say 0.5, then you have to make sure that you send it over two different paths or two different possible paths, because they can converge later on, at least two different copies. But when you do that, when you split and send the information to different nodes, then you revise the reachability probability that are required for these copies, so that you do not constrain the resources or you do not strain the resources of the network further. Okay, so this one is a step that is required to create a manageable number of packets in the network. And whenever there is a congestion, obviously the packet with the lowest reachability probability will be dropped. So in our simulation studies, we have seen that actually the number of packets that coexist in the network using this is much lower than, let's say, if you were to use speed alone. And we can carry much higher number of, significantly higher number of flows in the network at the same time. So this really works if you combine it with probabilistic packet dropping. So
your experiments use sort of probabilities like 0.3, 4, 5, but I mean I see that's a sort of a...
Yeah, I see. So we have actually looked at two cases where we I mean, I'm going to talk about some of these results, but we had, let's say, a very high, relatively high reachability probability, 0.7, and the other was, let's say, the other one was 0.3, I believe. So those are the ones that we have used. If you go higher, obviously, then you end up creating a much, how should I say, a higher number of paths or number of copies per packet, then obviously the number of or the number of flows that you can support will go down as well. Oh, that's an obvious thing. Okay. And then for the, I mean, if these conditions change over time because you have a local prediction, then you compensate for the changes in those predictions as you go along in the network. So at the MAC layer, this is, so this is still, I guess, the reachability probability. Yeah, okay. So at the MAC layer, let's say you want to split the information and send send two different copies to two different or three different nodes. Here, the one with the star corresponds to the node that has that you will need to exchange handshake signals with. Let's say you send the data, let's say RTS, and then it sends a CTS back, and then the source sends the data once again to everyone, and the acknowledgement is sent back from J again. So here I and K are just listening to the channel and trying to catch up with the information. So if they don't receive any of these handshake signals or the data, they will simply keep silent but put a mark somewhere saying that, well, I have not received it. That was not a successful reception for me. And that information is sent to S when there's a handshake. For example, if the when sending a CTS, it will piggyback the information about how many packets it has missed, let's say, or how many packets it has successfully received. And we are also switching the responsibility for handshaking from, let's say, J to I to K to L, depending on what cases you see. Okay.
So what do you think the reachability probabilities are modeling? Are they modeling really just the digital communication of the packet? Like, there's, or are you trying to sort of use that as a proxy for maybe hidden terminal or collision?
So what we do is we are keeping track of the number of packets that we successfully receive and the number of packets that are sent. So each of the potential receivers keep in a moving window keep track of the number of packets they have received, and they report it to, let's say, S, and S already knows, for example, how many packets it has sent already. So the ratio of those will give you the reachability probability.
I'm asking is, like, if you think about a completely static situation,
Mm-hmm.
the MAC protocol works properly, each reachability probability is like probably close to 1 or close to 0.
Mm-hmm.
Right? Because digital communication tends to either be sort of an all or nothing kind of proposition.
Yeah, but I mean,
but there are other effects like, maybe people think, well, there could be mobility and the channel is varying the
So-
weight gain, or there could be collisions, and I mean there are some reasons to.
yeah, obviously. So
Huh?
What about conditions of those things rather than detailed?
Well, that's what I'm asking.
So, okay.
Let's see which what do these probabilities sort of physically try to capture?
Okay, so for example, one of the things that we want to capture is, for example, mobility is not something that we want to capture because we are looking at a relatively static network, so that we can actually create a history of local history of reachability probability. But there can be hidden, let's say, nodes that can affect that, and there can be external noise sources that we may have no control over, or due to the other objects in between that move around, the fading environment may cause the loss of packets too. So whatever the reason may be for packet losses is captured, is actually just observed, not even modeled here. I'm just observing what has happened. So if I do not exchange any information, for me, well, I may have very little sample point to make any kind of prediction. But if you exchange information relatively regularly, then you can come up with, I mean, if you have a one reachability probability, that's not something bad. But if you do, you can also have packet drops, for example. So packet drops will be accounted for in other functions in the network, but not in this case, though. So packet drops are handled differently than the physical and MAC layer losses of information exchange. So there is only one set of results that I would like to show. Here on this graph, you have, let's say, these four flows represented. Deadline 0.3, reliability 0.7, deadline 1.0 seconds, and reliability 0.2, and any combination of these four values. Okay, so one of them is obviously very low probability, the other one is relatively high, and the deadlines are 0.3 to 1. So what we see here is the following. On the x-axis, we have the number of flows, total number of flows that we can support in the network. On the y-axis, we have on-time reachability. The left figure shows what you would achieve with MMSpeed. The right figure shows what you would achieve with speed alone. That is not something that also accounts for delay in the network. And what we see here is these two graphs over here on the left-hand side, as long as they stay above this bar, then the on-time reachability, that is both meeting the timeliness requirement as well as reachability requirement, is satisfied for these two flows, or these two types of flows. And these ones over here show, as long as you stay above this lower red line, you will be fine. So here we see this critical point about 18 flows in the network for which some of the requirements have been violated. The same violation is here seen for 12 flows for the case of speed. So effectively, by getting rid of or exploiting some of the redundancies or some flexibilities that are envisioned by, let's say, low reliability flows, we can actually meet or allocate more resources for the ones that have stricter constraints. And this is basically a very coarse evaluation. We have a little bit more details results for, in our papers. Okay. So basically, the bottom line is, by trading or by getting some of the resources from the flows that don't require them and giving them to the flows that require them, you can actually accommodate more resources in the network.
So what kind of channel, how do you model your channels in producing results like this?
So this is actually based on JSIM simulator. So the JSIM simulator has a default channel model there. It's, I believe, a two-ray model, if I'm not mistaken. So we have not changed it. So we have just kept the simulators model. So JSIM is something that is developed by UIUC. Jennifer Howe. She has started working on that while she was at OSU, and then when she moved to UIUC, she continued working on that. Essentially, it's a Java-based simulator. And physical layer model is not very much different than what NS2 has. So it's a very simple model, admittedly. Okay. So, finally, I'm just going to talk very briefly about the QoS-based capacity estimation. This is really a lot different than what I have talked about so far. And this has something to do with the resource management as we can map it to the wireless multimedia sensor networks. The idea is if we want to make the resource management as centralized as possible, one of the ways, actually, let me not put it as decentralized, but as simple as possible without putting too much constraint on individual nodes, what you can do is you can actually try to estimate the capacity of the network in a central node and look at the network that you have, look at the demands that you have, and try to figure out if those demands can be met by the network. And obviously, it's a very tough question to answer. I mean, there have been many models so far that try to that have been used to predict the behavior of a network. What we are proposing here is definitely not directly applicable to what we have, what I have already presented, but it's just a first step. Just take it as a first step in that direction, because our work is still going on in terms of modeling the capacity, especially QoS-based capacity in multi-op wireless networks. So the availability of network resources, or the capacity, is necessary to estimate how many flows we can support in the network. And there's a group of work that has been proposed in the past, which looked at, for example, modeling of single-hop networks, so detailed analysis of throughput, delay, etc. And there is a body of work focusing on the multi-hop networks, and they usually give results such as data momentum, bit meters per second. But they really do not give you, for example, information such as what is the minimum delay that you can attain if you have to move, let's say, 200 kilobits of data in 2 seconds from one side of the network to the other side of the network. So the throughput and the delay variations here actually, that trade-off, or quantifying that trade-off, is our real motivation here in this work. So what we try to do is we try to model the network as a conductor plane, if the analogy is right. So we are not interested in the total kinetic energy, that is bit meters per second, sort of, that is inherent in the network, but we would like to look at the maximum heat transfer, so to say. Okay, so maximum bit meters per second gives you some information about the kinetic energy, and here we say, what if we want to move information or the heat from this side of the plane to that side of the plane? Okay, so this is more structured, obviously. It's a more controlled environment. So first of all, we try to create, we try to look at the system as an entity that carries flows. And in every flow, you have interference between transmissions that belong to the same flow that we call intraflow interference, and the interferences between different flows in the network, which we call the interflow interference. Okay? So for example, in this case, the orange arrows over here correspond to communication events that belong to the same flow, and the red ones similarly. And the interference of S2 on this white node over here is that corresponds to an interflow interference, and the interference of S2 on this white node over here corresponds to an intraflow interference. And we would like to differentiate those two. Okay. So what we do is, in order to model the system, if you look at a single flow, we would like to wait at the sources for a given period of time before we inject another packet into the network. Okay? So we assume that whenever a node receives a packet, it immediately transmits the packet to the next hop in the next time slot. So in order to reduce the interference effects of a packet that comes behind you, you basically wait a little bit, let the packet move in the network away from you, then you inject another packet into the network. And this causes the head of queue delay to grow. That is, the waiting time at the source grows as you wait more. For the interflow interference, you'd coordinate the packet injection timings given certain source placements. That is, let's say you have two sources that try to inject packets into the network, and they have to wait, let's say, 4 time units. Then you can make sure that they do not transmit at the same time, but when one of them sends at t equals 0, the other one sends at t equals 2, and the next transmission at t equals 4, etc. So you interleave the packet injections as much as you can. So we create a link model that is that says that the successful packet reception requires the signal SINR to be greater than a threshold value, and the probability of packet reception is modeled with this particular expression. And then the design strategy is to make sure that each link in the system or each transmission in the system satisfies this condition with a probability of 1 minus tau, where tau is a parameter that you would like to adopt for your system. So the hop distance ds to the furthest node such that the link condition is just satisfied is given by this inequality. Okay, so if you take it as an equality, then you have the furthest distance. And now we assume, for the sake of the start of the analysis, that our network is infinitely dense. That is, if I can find ds under this condition to be 5 meters, then I am guaranteed to find a relay node at 5 meters. This will lead us to find the optimal placement of nodes in the network. But for the time being, we assume that the density is infinitely large. Okay? So by knowing how the packets are expected to hop with the infinite node density, we can predict the positions too. So when we look at the packet hopping system and how the interference affects these, then we see that the distance between successive positions of senders can be modeled as an IIR hopping system, and we can find numerical results for that. And another observation is that if we have, let's say, packets going in the network hop by hop, then every packet injected into the network slows down the one in front of them. But this effect is not uniform, such that if you add yet another flow into or packet into the flow, then after a while, after several hops, this first packet simply escapes the rest of it, moves faster than the rest of the train, and therefore we can assume that we are only faced with 3 packets in the network. Okay, so we are only dealing with the 2 more leading packets in front of us. So if you have a 2D system, then you have flows. At least in our model, we have flows that are in parallel, trying to move data from one edge of the network to the other edge of the network. And now we have to figure out, first of all, how much spacing in time in terms of injection of packets into the network there should be. These are the deltas over here. These are the offset values. Secondly, we would like to see how far apart these flows should be, because if you put them too closely together, then you effectively have a combined rate of a single flow. If you put them too far apart from each other, each of them appears to be an independent flow, but the number of flows that you can maintain in the network goes down, therefore your throughput goes down too. So there is also a set of constraints that we will take into account for the interference between the flows in the network. So basically what we do is we try to find objective functions, or we define objective functions, let's say throughput or head of queue delay. Throughput is simply the number of packets that cross a particular border, and the head of queue delay is the waiting time plus the time it takes for a packet to be delivered to the destination. And we have certain constraints that are given as such. So we are interested in finding, let's say, optimal scheduling to inject packets into different flows, and optimal number of flows, or optimal flow separation, in other words. So this is another convex optimization function, and it cannot be solved properly with convex optimization techniques. But there's also a structure to the problem that we do not need to use brute force search algorithms. So what we do is, the problem formulation under trade-off model is to maximize the throughput subject to, let's say, head of queue delay constraints. Okay? So in that case, we find that the waiting time, from the waiting time, you can find these quantities as such, and M, the number of flows, and the range in which the displacements should be found. If they are given, then the S0, that is the first hopping distance, is found from the link conditions. And we would like to find the optimal combination of M and WS. Okay? So these are found numerically. So we basically formulate the problem and then use numerical optimization, very simple numerical optimization techniques to find them. So here in this figure, for example, the waiting window span WS is shown in meters, and here we have the number of flows. And what we do is, if you fix, let's say, this contour, let's say 1000, then you would like to find the tangent of these dotted lines, which touches this 1000 line, and that would be your optimal operating point. So here's an example. Here we are looking at a 500 by 500 meters. We look at we assume that there are 100 byte packets, and basically here tau is 0.5% or 5%, and head of queue delay we need it to be less than 0.2 seconds. That is the delay from head of queue all the way to the destination. And the optimal operating point under this condition happens to be this black dot here on this figure. And if you look at this point, then you see that the throughput is 241 kilobits per second, and the delay that you get is less than 0.2 seconds in this case. And this also gives us a separation between the nodes of 2.3 meters. So now,
head of queue delay is not exactly sure what is it an average.
Head of queue delay is the time a packet waits at the head of the queue plus the time it takes to reach the destination.
So what determines? Is it the question of you have these interference kind of constraints that dictate how long the packet waits?
Exactly. Yes, I mean if you inject your packet right away, let's say every other time frame, then the packet in front of you may be not far away enough, and it may be affected by the added interferer too much, and therefore its hopping distance may be much smaller than what it would be.
But how
So
are you accounting for the other interference?
the other interferers are accounted for by looking at the displacement of the packets relative to one another, and we are looking at in the numerical results we are looking at 2 more flows to up to and 2 more to low.
Schedule that says everybody
Should wait this much exactly.
Everybody. Okay, so it's completely solved in a centralized way.
Yeah. I mean this is nothing
So you
distributed.
said something about distributed. Right?
No. This is the
That's
distributed
fine. No,
would be the distributed would be if you could implement it really in the real network without any centralized controller. And by the way, this also assumes something else. There is no handshake, any kind of signaling involved here. We assume that every single time you send some data, it is received correctly if this if the SINR is larger than this threshold gamma t.
That part is okay.
Right? So, I mean, how this would translate to a more practical setting is a completely open question for me.
The threshold, I think, is okay. I think what is not changing in your model, right, is that your channel is not changing essentially. Right? I mean, you computed these static probabilities. Isn't that how you were modeling packet loss?
Yes. I mean, basically, you are saying that there's a Rayleigh fading model here involved, but obviously the parameters of that doesn't change.
It seems like there's multiple potential operating points. Or just think about the linear situation where how long this queue should wait for transit versus how long that queue should wait. It's not at all clear to me that the set of head of queue delays as a unique solution that
Well,
optimizes the throughput.
we have cheated there a little bit. We have cheated there a little bit. In order to find to make this work a little bit more tractable, what we said was that we solve the conditions for a single flow in isolation. Okay, then we assume that each flow follows that. Now we try to figure out how much apart they should be from each other.
So for a single flow in isolation, like a single flow in isolation means on one of those lines.
Yes.
Right? You have a complete characterization of the optimal head of Q delays.
Exactly. We just take the head of Q delays from there and let it be that.
Is that a dynamic programming problem you solve to do that, or is it turn out to be something simpler?
It is much simpler than that, actually. It's not too hard to figure that out.
Anything dynamic because he assumed essentially the packet error rate
Just setting up
is some p.
So basically, there is an optimal sweet point. I mean, you just look at different.
Do you do it sort of going backwards in some way?
Yeah, basically, we just wrote a very simple search algorithm to find the. I mean, there is only one minimum in that equation. I mean, I can show you the paper actually.
Okay.
It is very interesting. There is only one minimum point where the delay is minimized for a given set of parameters, and you find that point, and you assume that this is the waiting time for each of the sources for the 2D model. Now, when that is defined.
Is it that there's that every node, every Q on the line ends up choosing the same waiting parameter, or not? Or do they choose?
Well, only the source actually chooses the waiting parameter. The other ones simply receive the information and transmit right away.
Oh, okay.
Okay?
Yeah.
So only the source controls how much data will coexist in the network.
All right.
There is no buffering involved in the intermediate points.
So the other people just send automatically, and then the source chooses the
Yes, yes. There's only one knob that you're playing around with, and you have M nodes that operate the same way. The only thing is there's an offset between them. Okay? And obviously.
So maybe you are putting a knob at every node.
No. We are not putting a knob at every node. Only at sources. Okay.
But if they were not uniformly spaced, you might have to, right?
Well, actually.
Conservative knob at the source.
Yeah, I mean, obviously, but I mean, we find that if you put them in a uniform way, actually you can actually also maximize the amount of data that you can transfer across. Okay.
So I was going to ask you, how do you make sure that different sources inject packets, sort of coordinate?
I just assume.
Is it like
I just assume. Assumption is a very nice tool. Okay, so I'm not actually putting anything new. I mean, I am not saying how it should be done. I'm saying if it is done as such, then. Okay. So basically, this is just another thread of work that we hope will tie into wireless multimedia sensor networks in the future. And now, currently, we are working on detailed models on multi-hop communication across wireless network under, let's say, a service differentiation-based medium access control protocol such as 802.11e. And we hope that we will be able to model it for a larger network so that we can predict what we can achieve. For example, under given existing flows, how should we set the parameters of a flow so that we can get a particular throughput or a particular delay? That's what we are really after at this point. Okay. So, I mean, personally, I find this area quite open to new innovations and new techniques, and this is also an area which may be, look old to a number of people, because you may see a lot of the work that has been done earlier or traces of those works here as well. Right? So it's an interesting area, and I hope that I could just give you some introduction, or at least my perspective on the topic. Okay. Thank you very much for your attention. I have really taken more time than I should have, but thanks for your patience, and if you have any other questions, I would be more than happy to answer them.
Thanks.
All right, thank you.
So maybe they called you. I wasn't sure where you were, so I came. I showed up at about 12. It's probably late. I got here like about 12:40.
No, we went to